Alright, so as I was saying before I got cut off, there is a relationship between the voltage applied to the circuit by the battery, the current that flows through the circuit, and the overall resistance of the circuit. Now in this circuit there is just one lamp, so that is the only item that offers resistance to charge flow. And that relationship is called Ohm's law. And it's a pretty simple relationship. It basically says that the resistance is a ratio of the voltage applied to the circuit divided by the current that flows in the circuit. Now, we'll see more of this in the next chapter, but Ohm's law can be applied to the entire circuit, or it can be applied to individual parts of the circuit, for example, just the lamp. But in this chapter, we're going to look at very simple circuits where we only have one component that offers resistance to current flow. And that is either going to be a lamp or a device called a resistor, whose only purpose is to decrease current when connected in a particular type of circuit. But right now we're just going to talk about lamps. Now Ohm's law is most commonly written this way, and I believe it's written this way on your equation sheet. And again, V stands for voltage, I stands for current, R stands for resistance. And the unit again for resistance is the ohm. Something else that's worth remembering for Ohm's law, if I have only one item like the lamp, what I can say is that the voltage across the lamp is directly proportional to the current through the lamp. So these two items are directly proportional. So if we were doing an experiment to determine the resistance of a device like a lamp, if we made a graph that looked like this, where we plotted on the x-axis, well, let's just say we have many different batteries at different voltages. So we increase the voltage and then we could measure the current through the lamp. And so the current is a function of the voltage. So if we were to plot the current on the y-axis and the voltage on the x-axis, we would see that we would get a straight line, even though that's not terribly straight. But this graph would show a straight line, and the slope of this graph would represent 1 over r, because the slope is rise over run, which would be I over V. R is V over I. So if we were to find the slope would equal 1 over r. So this is one way we could determine the resistance of this lamp if we had a way to change the voltage and measure the corresponding current. So here's a very simple example of using Ohm's law in a very simple circuit where you only have one device using, or the current flows through. So you have a battery, you have a switch, you have wires, and you have a lamp. So the battery's voltage is 6 volts. It's connected to a lamp. The current is measured to be 2 amps, and we want to find the resistance. So using Ohm's law is very simple. Here's our equation for Ohm's law. V is equal to I times R. And if I solve this for R, I get V divided by I. And when I substitute 6 volts divided by 2 amps is 3 ohms. So the resistance of our lamp is 3 ohms. So using Ohm's law is very easy when you only have one component, that being the lamp in the circuit. Our last topic in this chapter is called electrical power. Now, if you remember, mechanical power in the earlier part of the year was the rate at which work was done. There's a slightly different definition for electrical power because there's really not any mechanical work being done. There's no forces acting on objects, no displacement by the objects. But there is a term for electrical power that we need to be familiar with, and the definition is a little different, and this is it. It's the rate at which energy is used and or delivered. So again, electrical power is the rate at which energy is used or delivered by a circuit or to an individual component of the circuit. The equation for power is I times V, and the units are the same as they were for mechanical power, that is the units or the watts. Now if we just use the units for current, which are amps, for voltage, which are volts, an amp, if you remember, is a coulomb per second, a volt is a joule per coulomb. So if I multiply those two together, the coulombs cancel and I end up with a joule per second. And that is a watt as we defined it earlier in the year. So when you hear the word watt with electricity, you probably think of light bulbs. And an example is a 60-watt bulb, which is giving you the power rating. Now, with light bulbs in your house, they're all designed to operate with a voltage of 120 volts. So when you plug a light into an outlet in your house, the outlet supplies 120 volts across that 60-watt bulb. So just using this simple equation, you can determine how much current flows through that 60-watt bulb. And again, the 60 watts means that that light bulb, when it is on, uses 60 joules of energy every second. Now with the power equation, we can combine it with Ohm's law to express power in two other forms. Now on the equation sheet, this is the form that appears for electrical power, and this is Ohm's law. But if you notice, if we substitute I times R in for V, we'll get I squared R. And another way is to substitute for I. If I solve Ohm's law for the current, it becomes V over R, and if I make that substitution in here for I, the V's will square, and I'll get V squared over R. So these two equations are not on the equation sheet, but you should know how to derive them by combining these two equations. So if we go back to the prior example, and in addition to determining the resistance of the lamp, if we wanted to know what the power used by the lamp is, we could simply use the equation for power. Since I know I and V, those two pieces were given, 2 amps times 6 volts would be 12 watts. So that means that this lamp uses 12 joules of energy every second. So another question that might be posed is to find the energy used by the lamp in 15 minutes. Now, a very generic energy power equation that can be used in any circumstance is that the energy is equal to the power times time. Because remember, power is the rate at which energy is used. So if we just multiply both sides of that equation by time, we get power times time. So if power is measured in watts and time needs to be measured in seconds, we can determine the energy used. So if we want to find the energy used by the lamp in 15 minutes, we can use this generic equation, and we need to convert minutes to seconds. So if I multiply 15 times 60, that will give me time in seconds, and then I multiply that times 12, and that will come out to 10,800 joules. So this covers the first 5 sections of Chapter 18, the only sections that we will cover, and I will post a worksheet on Google Classroom so you can get some practice using some of these equations and some multiple choice questions as well.